So today's learning intention is looking again at stationary points of a curve, but this time we're going to focus on particular points of inflection. Now our National 5 essential skills are factorising and substitution. So let's get started. Now you saw in the previous lesson all about stationary points. So some points in a curve are neither increasing or decreasing but are stationary. These are called turning points in a graph. This means the gradient of the tangent to the curve is 0 at a stationary turning point, and we can find them by solving f dash of x equals 0 or dy by dx equals 0. So what we're trying to do is find out where the gradient equals 0 on the curve. Now there are 4 possible turning points, and we've already looked at maximum and minimum turning points. So today we're going to look at horizontal points of inflection. We can either have rising points of inflection or falling points of inflection. Let's get started with an example. Example 1. Find the stationary points and determine their nature for the graph of f of x equals x cubed minus 3x squared plus 3x. So again, to get ourselves started, left hand side, let's have a look at the gradient of this curve, what's happening. So we're going to have to calculate the derivative, f dash of x. So f dash of x equals 3x squared minus 6x plus 3. And for stationary points, let f dash of x equal 0. So we need to write out 3x squared minus 6x plus 3 equals 0. And we have to factorise this to find the x coordinates of the stationary points. So to make life easier, I'll take out a common factor of 3. That gives me 3 times x squared minus 2x plus 1 equals 0. So now I have to factorise the x squared minus 2x plus 1. And that gives me 3 times x minus 1 equals 0. When I solve this, that gives me a point of inflection, a stationary point at x equals 1. How do I know it's a point of inflection? Well, when I look at the second derivative, f double dash of x, that equals 6x minus 6. When I sub in x is 1, I've got the second derivative at x equals 1 is 6 minus 6, which is 0. So when the second derivative equals 0, that tells me I've got a point of inflection. Previously we've looked at where the second derivative is positive, where it's negative, but now it's 0. So that flags up I've got a point of inflection. So I want to know exactly where this point of inflection is. So I'm going to take x equals 1 up to the right hand side of the page and back to the function f of x equals x cubed minus 3x squared plus 3x. I sub in x is 1, that gives me y equals 1. So I know I've got a turning point, it's a point of inflection at the coordinate point 1, 1. But now I need to know, is it a rising or a falling point of inflection? What's its nature? So to do that, I'm going to draw up a nature table. Okay, now in the top line of your nature table, you're going to think about the x coordinate. So I put in x. In the middle column, I'm going to put in x is 1, because that's where I know the location of our turning point is. And now I'm going to have a look at what's this function doing as I'm approaching 1 and as I'm leaving 1. So particularly let's look at the gradient of the curve. So f dash of x equals 3x minus 1, x minus 1. And it's better to put in the factorised form, it's just easier when we're doing our calculations. Now, I don't have to calculate, I already know that the gradient is 0 at x equals 1, because that's where our turning point is. So I can just put that straight in. So let's now think of a point that's just on the left hand side of 1 as we're approaching 1, going from left to right on our curve. So let's think of the point when x is 0. What's happening? So when x is 0, sub that into the derivative, 3 times x minus 1, x minus 1. So that gives me 3 times nothing minus 1 times nothing minus 1. So minus 1 times minus 1 is 1, times 3 is 3. And that's positive. I don't really need to know the value, I just want to know, is it positive or is it negative? So it's positive, and I can put that into the nature table. Now let's think what's happening on the other side of 1. Okay, we've gone from 0 to 1 to, so let's think about 2. When x is 2, what's the gradient doing? So I'm going to put x equals 2 into the derivative, 3 times x minus 1, and that gives me 3 times 2 minus 1 times 2 minus 1. So 2 minus 1 is 1. So I've got 3 times 1 times 1, which is just 3 again. And again, I don't really care about the value. It's just, is it positive or negative? So it's a plus 3. It's positive. So I can put that into my graph, into my nature table. So now let's look at the shape of the curve. What's happening? It's a positive gradient. I've got a 0 gradient at x equals 1, and then I've got a positive gradient again. And that now gives me a rising point of inflection at the point 1, 1. So let's take a look at this function. What does it really look like? So here I've graphed it for you. It's a cubic. It's a positive cubic. It's rising, turning, and rising again. So I've got the function x cubed minus 3x squared plus 3x, and we can see on the graph the rising point of inflection at the point 1, 1 as shown. So let's have a go at another example. Example 2. A curve has equation y equals 2x cubed minus 6x squared plus 6x minus 5, and I want you to find the stationary points and determine their nature. So again, start the exact same way. Let's think about the derivative of this function. So on the left hand side, I'm looking about the derivative. Now in this case, our notation's changed. I've got y equals 2x cubed, so I'm now going to have derivative notation dy by dx. Now be very careful to keep your notation correct in context. So dy by dx, the derivative, equals 6x squared minus 12x plus 6. Again, we must state, for stationary points, let dy by dx equal 0. So that gives me 6x squared minus 12x plus 6 equals 0. And we're going to have to factorise to find the x coordinates of the stationary points. So again, make life easy for yourself. I can take out a common factor of 6, and this gives me the exact same as before. I've got 6 times x squared minus 2x plus 1 equals 0. Factorising that gives me 6 times x minus 1 equals 0. And solving gives me x is 1. So I've got a stationary point at x equals 1, and I want to just verify the nature of that stationary point. So I'll look at the second derivative. In this case, the notation is d2y by dx squared, and that equals 12x minus 12. So I've differentiated dy by dx. So when x is 1, d2y by dx squared equals 12 minus 12, which equals 0. And remember, when the second derivative equals 0, that tells me I have got a point of inflection. I'm just going to call it POI. But where is this point of inflection? Well, to find that, I'm going to take x is 1 and substitute it into the right hand side here to the function, to the original function, y equals 2x cubed minus 6x squared plus 6x minus 5. So when x is 1, y equals minus 3 in this case. So I have got a stationary point at location 1, negative 3, but I need to know what type of point of inflection is this. Is it a rising point inflection or a falling point of inflection? So to do that, I'm going to have to work out a nature table. So can you remember what that looks like? So it's a little grid. The first line in your grid, I want you to think about the x coordinate. Now our turning point is at x equals 1. And then we have to consider the shape of the curve approaching 1 and leaving 1. What's the gradient doing? So if I want to work out the gradient, I have to know the derivative. So derivative equals 6x minus 1, x minus 1. Now we already know the derivative is 0 at x is 1, because that's where the turning point is. So I can just put that straight in. But what's happening is I approach 1. Okay, right next to 1, what's happening? So in this case, I'm going to look at when x equals a half. So when x equals a half, put it into derivative. I've got 6 times a half minus 1, a half minus 1. Now a half minus 1 is minus a half. Times minus a half is plus a quarter. So I've got 6 times plus a quarter. Now I don't have to work that out. I just have to understand that that's a positive number. Okay, and I put a little plus sign in my grid. So what's happening on the other side of 1? So let's make life simple. Let's just look at when x is 2. So I've got 6 times 2 minus 1 times 2 minus 1. So that's just 6 times 1, which is 6. But again, I don't really care about the value. I just need to know it's positive. And I put my little positive sign in. So what's the shape of the curve? Well, the gradient is positive, it's 0, and it's positive. And that again gives us a rising point of inflection. So I can write that up the top. So I've got a point of inflection, rising point of inflection at the point 1 minus 3. So let's look at the curve. So it's 2x cubed minus 6x squared plus 6x minus 5. Again, you should understand that's a cubic. It's a positive cubic. The coefficient of x cubed is a plus 2. So it's going to be rising, turning and rising again. A positive cubic. And we have here a rising point of inflection at 1 minus 3 as shown on the curve. That's where the gradient has gone to 0. Right, try this example on your own. It says find the stationary point and determine its nature for the graph with the equation y equals minus x cubed minus 3x squared minus 3x plus 10. Now beware, warning here. What's the coefficient of x cubed? Yep, it's a minus 1. It's a negative cubic. Now can you jot down what does that look like? You should have in your head roughly what that cubic looks like. Okay, now think about it before you get started. I'm going to come back later on and give you a full explanation, a full worked example for this, but just try it just now. Right, here goes. Here's our full worked example. Find the stationary point and determine its nature for the graph with the equation y equals minus x cubed minus 3x squared minus 3x plus 10. Again, we start these questions the exact same way each single time. I've got notation y equals, so our derivative is dy by dx. It's in context. So left hand side, let's look at the derivative. So dy by dx equals minus 3x squared minus 6x minus 3. Again, we must state for stationary points, let f dash of x equal 0. That should read dy by dx equals 0. Please change that in your notes. So I've got minus 3x squared minus 6x minus 3 is 0. Again, let's make life easy for myself when I'm factorising this. Take out a common factor. Okay, you need to factorise to find the x coordinates of the stationary points. So I've taken out a common factor of minus 3. That gives me minus 3 x squared plus 6 plus 2x, plus 1. So look, the signs have changed. If you're not sure, multiply that bracket out again just to make sure you're correct there. Now I have to factorise x squared plus 2x plus 1, and that gives me minus 3x plus 1 times x plus 1. Solving that gives me a stationary point at x equals minus 1. So now check the nature of it. So d2y by dx squared, second derivative, tells me the nature of my turning point. So d2y by dx squared equals minus 6x minus 6. I'm going to sub in when x is minus 1. d2y by dx squared equals minus 6 times minus 1, which is 6. 6 take away 6, which equals 0. So when second derivative equals 0, I know I have a point of inflection. But where is that point of inflection? So I'm going to take x equals minus 1. Back up right hand side, back to the function y equals minus x cubed minus 3x squared minus 3x plus 10. And I'm going to sub in x is minus 1 into that equation. Now double check that for me, but you should get y equals 11. Now that tells me I have a turning point at minus 1, 11. But what is that turning point? Okay, is it a rising or a falling point of inflection? So to work out the nature of my turning point, I'm going to use a nature table. So again, your top row of your nature table, you put in your x values. So the turning point is located at minus 1. So I want to know what's happening round about minus 1 as I approach minus 1 and as I leave minus 1. So a number less than minus 1 and a number bigger than minus 1. So what's happened to this curve? What's the gradient look like? Well, the derivative is minus 3x plus 1 times x plus 1. Now we already know the derivative equals 0 at our turning point, so I can just put that straight in. So let's think of a point a little bit smaller than minus 1, to the left of minus 1 if I was drawing the curve. So I'm going to think of what's happening when x equals minus 2. So I'm going to put minus 2 into the derivative, minus 3 times x plus 1, x plus 1. So that's minus 3 times minus 2 plus 1 times minus 2 plus 1. If you work that out, you should have the derivative equals negative 3. Now I don't care about the value, I just want to know that it's negative, so I put a wee minus sign into my nature table. So the gradient's negative as I approach minus 1, it's 0 at minus 1, so what's happening? A number bigger than minus 1. So let's think about what's happening when x is 0. So I sub x is 0 into my derivative, and that gives me again the value negative 3. I don't care about the number, it's just the sign, so it's negative, and I can put that into my nature table. So let's jot down the shape of our curve. Our shape has got a negative gradient, a 0 gradient, and a negative gradient. So it's going downhill. It's a falling point of inflection. So I've got a falling point of inflection at the point minus 111. Now what does that look like then? A little look. Here we go. I've got the function here, y equals minus x cubed minus 3x squared minus 3x plus 10. It's a cubic, it's a negative cubic, it's decreasing, it's turning and it's decreasing again. But we've got a falling point of inflection at minus 111 as shown here. Right, self-assess your progress. How did you get on with this? Did you find it easy, green, okay-ish, amber, or are you struggling with this and you're going to mark yourself red? For extra work, you might want to take a quick look at page 106, exercise 6M in your textbooks. We've learned about points of inflection. Key steps were that we differentiate the curve's equation, we set the derivative equal to 0 to find where the stationary points, the turning points, are. Again, we factorise and solve to find x coordinates of the stationary points. This is just the same for any stationary point question. We find the second derivative and insert x to determine their nature. If the second derivative is 0, you must draw a nature table to determine the nature of the turning point, because you will have a point of inflection. Substitute x coordinate into the curve equation to obtain the y coordinates, and state the coordinates of the turning point and their nature to fully answer the question. Make sure you've taken all your notes down before you finish off this video. Thank you.